All right, so today we're going to be talking about modeling and optimization. And in reality, these two are just special applications of derivatives, and that's why it fits very nicely into whatever we've been doing so far. So, yeah, we're going to be talking on modeling and optimization. And today is just mostly going to be about how we can look at a problem and use derivatives as a tool to solve these problems. And there's really not much new concepts to be learned. So let's just get into it. It's just a bunch of problems. So problem one, we are given a 20 by 25-inch rectangular sheet. How do we cut X inches off each corner in a way to maximize the volume of the box from the leftover sheet. So what this problem's trying to say is we're given this rectangular sheet, right? And not to scale. So the height, I guess, is 20 inches and the width is 25 inches. And we're going to be cutting X inches off of each corner. So we're going to make X by X inch cuts on each corner. And you can kind of imagine that the leftover like surface that we have formed over here can be made into a box, right? Because we can take these things and then fold over there, and then so these like rectangular strips over here become flaps, and that can kind of make our box. And so we want to maximize the volume of the box that can be made by cutting these X inch strips. And so how do we go about this problem? So the first thing that we're going to do is first represent the volume once we cut off X inches, right? So what's the volume going to be? Well, our volume of like a we know that the volume of like a rectangular prism is just the width times height times the base, right? And so over here the base, or like this base is going to be 20 minus 2x because we're cutting off an x over here and an x over here, right? And our height is simply going to be x, right? Because that's the strip that we're going to be cutting. And then the width is similar, where we had a 25 inches and we're cutting off x on both sides. So we have 25 minus 2x. And so that is a resulting volume. And the problem asks to maximize this volume, right? And when we learned about extreme values, like that's like the way to find extreme values, that's going to be very useful in this case, since now we really just have an equation and we just need to find the maximas of that equation, and whatever x that satisfies that maxima are going to be what we use, right? So now we have this equation and we're simply maximizing the value of this equation, or we're trying to find the x that value maximizes the value of that equation. So let's take the derivative of it, because that's how we're going to find critical points. So dv over dx. Well, before I can find the derivative, let me write this equation in a way that makes finding the derivative easy. So I'm just multiplying the x and this equation. So I get 20x minus 2x squared times 25 minus 2x. And now I'm going to use the product rule to find the derivative. So dv over dx is simply equal to 20 minus 4x times 25 minus 2x, and then plus minus 2 times 20x minus 2x squared. And then simplifying all of this, I get 20 times 25 is 500 minus 40x minus 100x plus 8x squared. And then simplifying this other side, I get minus 40x plus 4x squared. And then simplifying all the terms, I get 12x squared, right? Because you have this and this. And then this is minus 40, minus 140, minus 180. So 12x squared minus 180x. And then this is the only constant term. So plus 500. And so to find the critical points, we have to find out where this derivative is equal to 0 because, or where it's undefined. It's clearly not undefined in any domain. So let's find out where it's 0. And so to find out the zeros of this, we can utilize the quadratic formula, right? So using the quadratic formula, we have negative b. So 180 plus or minus square root of 180 squared minus 4 times 12 times 500 divided by 2 times 12, right? And if we were to solve, if we were to like, you have to use a calculator to simplify this, and I think looking at my calculator, I'm getting x is equal to 3.68 and x is equal to 11.32. So these are the critical points, and we know that x equals, well, firstly, we'll have to test which one maximizes the value, but the good part is we know that x equals 11.32 is not a valid point in this model that we have, because if x is 11.32, then like over here and here, if you add that up, that's going to be more than 20, right? And so that value is just not permissible for our model. So we only look at this value, and when we see the volume when x is equal to 3.68, we get the volume is about 820, and that's the maximum volume we can get. And you can find that by just plugging it into our original equation. So this is like an example of modeling, and we see how like what we have learned about derivatives and how it can be used to find maximums and stuff is very helpful in this case. So let's look at another problem, another optimization problem. And here, so problem 2 asks, find the dimensions of a 1,000 centimeter cubed cylindrical tank that minimizes surface area. So in this optimization problem, we're given that we want to make a cylinder, or like a right cylindrical tank. So we have a tank that looks like this, right? It's a cylinder, and the volume of that tank is equal to 1,000 centimeters cubed. And we have to achieve this volume by minimizing the surface area. So how do we get this volume with the minimum surface area? And that's the gist of the problem, right? And so let's recall some of the geometry, like the geometry of a cylinder. We know that the volume of a cylinder is given by pi r squared times h, and that is equal to 1,000. And the goal is to minimize the surface area. So surface area of a cylinder is equal to 2 pi r squared plus 2 pi rh. And the way you get that is you have the two circles, right? And so those are two circles, and so the area for the circle is pi r squared, and then because of the two circles, you have 2 pi r squared, and then you have to account for the surface area of the whole like cylinder and compass, right? And so you can kind of, if you unroll that, you get the width is 2 pi r, and then h acts like the height. And so that's how you get the surface area of a cylinder. And so the goal is to minimize this surface area while hitting the constraint that pi r squared h is equal to 1,000. And so this problem is kind of unique because it has two variables. We have r and h, right? And we've only really dealt with single variable calculus, and we'll use that to solve this. And so how do we make sure that we get only one variable? Well, we can use this constraint and remove a variable, right? If I solve for h, I get h is equal to 1,000 divided by pi r squared. And then I can use that value for h and I can plug it in here, and now I'm only getting one equation. So I get surface area is equal to 2 pi r squared plus 2 pi r times 1,000 divided by pi r squared. And then after some simplification, I get 2 pi r squared. You can cancel these, and then I get plus 2,000 divided by r. So that's our surface area. And essentially, we want to find the minimum value that this equation takes on, right? And so again, when we want to find mins or maxes, we should find the critical points. So let's find the critical points. And how are we going to find the critical points? Well, the first thing that we do is find dSA divided by dr, or dSA over dr. And so to find that, we get 4 pi r plus negative 2,000 over r squared, right? And then, so simplifying that, 4 pi r minus 2,000 over r squared. And we want to find out where this is equal to 0 or undefined. We know this is undefined at r equals 0, but clearly that won't give us 1,000 for our volume, so we'll ignore that case. But let's solve for it when it's 0. So 4 pi r is equal to 2,000 divided by r squared, and then taking r squared to the other side, that gives us, so let me continue this over here. That gives us 4 pi r cubed is equal to 2,000, and then r cubed is equal to 500 divided by pi. So r is equal to the cube root of 500 divided by pi. And we know that this is a minimizing solution, because if we were to graph out if we were to, like, again, remember how we want to analyze what kind of extreme solution this is. So if we were to graph out dSA and then look at SA, right? When r is less than this value, so when r is less than that value, we know that the derivative is when r is less than, or when r is less than that value, we know that the derivative is negative, because, like, let's just take 0 as r. You get 0 over, or let's take like 1 as r, for example. We get, this is like 4 pi, and this is like negative 2,000, right? And so it's negative, and then after, when r becomes greater, like we can take r towards infinity, then this becomes like 0, and this is like a positive value, right? So dSA will be positive, and so the way that our surface area function behaves is it decreases first and increases later. And we know through the first derivative test we have a minimum. So r equals cube root of 500 divided by pi is a valid minimum, and so that's the solution to this problem. Let's do one last optimization problem. And so this problem says, problem 3. This problem says, what is the largest area a rectangle can have, which is inscribed inside one arch of the sine function. So essentially what it's saying is, we know that when we graph out a sine function, it looks like this wave, and this is like one arch of it. So you can think of like this as one arch of it. And without loss of generality, it doesn't matter what arch you take, because these arches are like all equal in area. But in one of these arches, we're going to inscribe a rectangle, and we want to find the largest area of a rectangle we can inscribe inside of an arch or sine function. So let me just draw out a sine function, like an arch that looks like this, and we're just trying to inscribe a rectangle over here. So when we inscribe a rectangle, right, the area of a rectangle is given by this height and this width, right? And so the height is clearly just gonna be some function, like the height of it is like determined by where on this like sine arch it is, right? So if this if this length over here before the rectangle starts is x, then the height of the rectangle is going to be sine x, right? And because the arch is kind of congruent, if I like draw it through the middle, then but because it's like symmetric in that sense, then there's going to be x from over here as well, right? And so what happens is um, the width ends up becoming pi minus 2x, because one arch is length pi, because half the period of sine is pi, right? So if you have sine x over here, this is pi, this is 2 pi, right? So one arch is of length pi, then one arch is of length pi, and if we were to create a rectangle that starts after some length x, we have height sine x, and the width of the rectangle is simply pi minus 2x. And we can say that because if we were to sort of draw a line like in at the midpoint of the arch is symmetric. So on the other side also, we're sort of leaving off x, and we're gonna have the same height over here being sine x. So now we have formed we have all the information to form an equation for the area of the rectangle. So the area of a rectangle is simply going to be pi minus 2x times sine x. And like with all the other previous problems, we just have to find the maximum of this. So again, let's find the critical points. And so let's do dA over dx. And so again, I'll utilize the product rule. I get minus 2 times sine x plus pi minus 2x. And then the derivative of sine x is simply cosine x. And simplifying, I get minus 2 sine x plus pi cosine x minus 2x cosine x. And now now you have to find out when this is equal to 0. But it turns out that in this case, you cannot use any analytical tools to find out where it's 0. And so you'd have to use graphical tools to find out where it's 0. And basically, you'd graph this out, find out where it's 0, and you only have to look at one period of it. And you'd see that when x is equal to around 0.71, you get a 0. And that turns out to be a valid maximizer of the area. So the maximum area you can get is pi minus 2 times 0.71 times sine of 0.71. And obviously this is going to be radians, right? And so that turns out to be around 1.12 square units. So the goal of this lecture or video was just to show how the tools that we've learned by learning derivatives are very powerful, and they can help us solve these sort of optimization problems where we want to find the max and mins of various scenarios. So in reality, just the tools, you're going to be using derivatives at the end. The hardest part is coming up with this like model of how translating what the problem's asking into the model that we want to create. And once you've created the model, then the mechanics is very like similar in all the cases, where you just have to find the derivative of the equation and then use the first derivative or second derivative test to just see if it's a valid maximizer or minimizer, and always like checking back at the original model to check if the values for x that you found and the values for minimizers or maximizers that you solved for actually make sense and in the given domain and the constraints of the original optimization problem.